Okay, so actually this is the third class for this course. And from last class, we have started to study on the face detection algorithm. Okay. Especially, there are many papers and many different approaches, but especially we want to focus on this one, the cascaded AWS algorithm. So again, as we have already discussed, this algorithm is implemented in OpenCV, and that's make also the make it very famous. And it is working very fine. If you any of you have tested OpenCV, you know it is very fast and relatively very stable and accurate. So algorithm is one of the most popular and famous algorithm for face detection. So by the way, it is not just for face detection, actually. So it also can be used for other object detection as well. Okay, yeah. So the core title of the paper, when it was first, published, was rapid object detection using a boosted cascade of simple features. So it is actually explaining um, the important features of this paper. So it was developed, uh, proposed by Viola and Johns. So some people call this one as Viola and Johns algorithm or cascaded data boost. Uh, yeah, something like that. So, especially from today, we are going to investigate this algorithm very in detail because by understanding this one very representative algorithm in detail, uh, you can understand, how the face detection is working in detail. Even though, there are some other approaches. For example, some other, different approach may use neural network or some other approach, but they have much in common. So if you understand this algorithm, then other approach can be easy to easy to understand. Okay. Okay. So actually, in this algorithm, I think we have briefly mentioned last week, but the main key idea is like this. Okay. So first of all, this algorithm is using machine learning approach. So this is kind of machine learning, algorithm to detect any object. Not any, but mostly face, but it also can be used for other objects. Have you seen any other example? This OpenCV uh, cascade cascaded data boost was used for uh, detecting any other object other than face. Anybody has seen any example from paper or from YouTube, whatever? Yes, cars. Yeah, not just for cars, for kind of traffic system kind of stuff. Orange ball, simple orange ball. Yes, there is also one very popular, example code of OpenCV for object, tracking. It is normally for object tracking because orange ball is using color information for detection, so it doesn't. It is not using actually this algorithm. Okay. Yeah. So yes. So there are some example applying this algorithm, especially using OpenCV training algorithm functions for cars. So some guy tried to detect cars using this algorithm and OpenCV function. So first of all, it is using machine learning approach. So we have to understand this algorithm. We have to understand the learning process of this algorithm. So we will take some time to understand how it is learning, okay? How it is training the data. Okay, so this is one important part. The other one is, it is using a new image representation. It is called as integral image. So this is not any very serious theory. It is very simple kind of, transformation of image, very just adding some value kind of stuff. But the main purpose of this approach is to speed up the feature evaluation, feature calculation. Okay? So as for feature, we'll discuss more in detail later. We are using car-like features. So the feature itself is very simple. To calculate the car-like feature very quickly, this interior image is very useful to speed up this special, feature calculation, car-like feature. Okay, so this is one of the key contribution of this paper. As for machine learning, it is using a kind of AdaBoost-based algorithm, but it is a little bit kind of modified version of AdaBoost. So we also try to understand this learning algorithm. And lastly, one more important contribution of this paper, it is combining, cascade classification system to this, AdaBoost, training system. So cascade is combined to this AdaBoost. So that's why we are calling this algorithm as cascaded AdaBoost algorithm. Okay. Yeah. So once when you want to understand this algorithm, it is not a kind of simple one, but when you want to understand this, cascaded AdaBoost algorithm, you have to understand these three parts. The feature part, first one feature, it is using integral image and car-like feature. So you have to understand how they are calculated. Okay? And the second step is to understand the AdaBoost training part, learning part. And then you have to understand how cascade approach classification is applied for this AdaBoost. Okay, that's all we need to understand for this algorithm. Okay. So today we'll start from the feature. Okay, integral image and highlight feature. Okay. Okay, so this picture page is showing the diagram of the whole system, how it is processed from the original image and how it is, generating the final results. Okay. So when the original image is input to the system, then integral image. So we haven't studied about integral image yet. Okay. So let's assume, it is a kind of a little bit modified processed image. Okay. So integral image is generated. And then based on the integral image, the feature, car-like feature, is calculated. And these calculated car-like features are fed into the AdaBoost system for feature selection. So the main role of AdaBoost, training procedure is to select good features among many, among a big set of features, car-like features. Okay. And then these selected features are fed into cascaded classification, structure, and then it can classify very efficiently, very quickly. Okay, so that is the overall, training framework. So finally, what we are generating through this, training is the final cascaded AdaBoost structure. So AdaBoost procedure training, learning procedure is generating some good features, a set of good features, critical features, and then cascade classifier is using those selected features to make the final classification structure. So finally, it is generating a kind of classifier. It's not a simple classifier, kind of a little bit complicated classifier system. Okay? And then once the training is done, we can use this classification system to detect, faces or any other objects. Okay. Any question? Okay, so once the classifier cascaded classifier based on AWS features is generated from the previous training process. Okay, then this classifier is applied to the image, the picture, to find the face, to find any number of faces. Okay, so this slide, I'm looking at slide number 5, is explaining, how the classifier can be applied in real time to detect faces. So this is kind of application of cascaded classifier. Okay. So I'm assuming we already have trained classifier, and we have this cascaded classifier. Okay, we'll study how to generate it later. Okay, but let's assume we already trained this cascaded classifier. Then the main, the general process to detect face is, inside the whole picture, we are placing some small window. Here, the small window is a kind of candidate region of face. So in the beginning, we have a picture, but we don't know where is the face. Okay, so this small window is scanning from left top corner and to the right bottom corner. Okay, left to right, top to bottom direction. So it is kind of scanning. Okay, and every region, when this window is scanning, every region region of the position of this window, we are taking the region as a small image. Like, for example, in this face area in the middle. Okay, so there is a window. So I took the window of the face. Okay, so it is regarded as a kind of small image. Okay, similar to the training images. We'll see the talk about the training images later. So the training images, is training database is composed of positive and negative samples. So positive sample means just face image like this. Okay, so we are cropping this region of window, then this face image or any background image. Okay, every window image is fed into cascaded classifier. Then this classifier determines, oh, this is face when it is face, right? When this is background, then it is supposed to say, oh, this is non-face, yes or no. Okay, so basically it is kind of binary classification. Okay, so in this sense, we can say, we are applying this trained cascaded classifier to every small region, every window region of the whole picture by scanning the window from left top to the bottom corner. So it is testing, simply saying it is testing all the small regions to check if it is face or not. Okay, so this is how the face detection process is happening. Okay, so different from identification, this kind of process is actually a very big difference between detection and identification. In case of identification, face identification, oh, I want to know who is this woman, who is this guy. Okay, then we are assuming we already have the face image detected by face detection. So we don't need to scan the whole image, right? Because that is the purpose of identification. But in case of detection, it means we want to find the defined object like face or car in the picture. So it means we don't know where it is. So we have to search the face region in the whole image picture area. Okay, so this kind of scanning left top to right bottom is the kind of very typical way to search the image. Okay. So Penaganti has a question. Cascaded classifier is used to detect any kind of object. Okay, so if you train this cascaded classifier for a face, okay, so it depends on the training data. Okay, oh, I want to detect a face, then you have to train this classifier with face images. Then it may classify faces or may not, depending on the accuracy of the classification training. Okay. If you train this classifier using car images, then you may produce a kind of cascaded classifier to detect cars. Okay. If you have any other type of object you want to classify, or for example, if you want to classify chairs, then you can also train the cascaded classifier using chair images. Okay, so this is how it is working. But it is not working for any object. Okay, it is working. Some type of object is good to be classified by this kind of classifier, cascaded classifier, but some kind of objects are not good. So it depends on the property of the common property of the object. Okay. So first of all, the object should be rigid body. I mean, even though our face has some different expression or different shapes, patterns, but it has very common homogeneous kind of patterns. So for example, we have two eyes in the middle and upper, a little bit middle upper area. We have nose in the center, right? We have mouth at the bottom, region. Okay, we have ears on both sides, right? In this way, we have very common, even though we have very different faces, but we have very common structure. So this basic pattern is not changing a lot. Okay, is clear? Yeah. Then in this kind of very rigid and structured object, it is easy to be classified by this cascaded classifier, and especially this algorithm. Okay. But if you are dealing with very non-rigid object, flexible object, then this classifier may not produce any good performance. Okay. And another question from Rawa is, it is using correlation or Euclidean distance or another, or just template matching. Actually, this algorithm is not just calculating the distance, like correlation or Euclidean distance. Okay. So it is not like just calculating distance and selecting the minimum distance one. Okay. So that is just very. For example, if you are using template matching, right? Then you are template matching and calculating the distance, like using Euclidean, and you can select. You can give some threshold, and you can select some small distance object, right? That is very basic approaches. But this algorithm is not using that kind of basic approaches. It is again based on machine learning. Okay, so the classification, the determination. Oh, is it face? Is it close to face? Okay, so it is. If this image has a similar feature as face in terms of distance? Okay. So anyway, so to determine this kind of decision, it is using the learning system, machine learning algorithm, instead of calculating the distance directly. By the way, the machine learning algorithm is using some distance measure inside. So it is using kind of Euclidean like distance measure to calculate the error kind of stuff. But it is not the main part of this algorithm. Okay. Any other question? Okay, so it's good. So whenever you have because this algorithm is very kind of a little bit relative to other image processing kind of approach, it is a little bit complicated. Okay, so it is important for you to understand every step clearly. So whenever you have any question, okay, just type in the chatting window. So I'll try to answer the question. Thank you. Thank you for the good question. Okay. So anyways, this is the general process. Okay, when the cascaded classifier is ready. So remember, when we have finished the whole training stuff, okay, so we have to apply this classifier to every window region of the whole picture. Okay, so that is the overall setup. Okay. Okay, so now we need to understand the very details of this training process, because this is the main part of core of this algorithm. Okay, so to understand the training process, I want to introduce a few important concepts. Maybe some of you already know this concept very well, but I want to make sure everybody understands this concept, because if you don't know this concept, it may be very confusing to understand the algorithm itself. Okay, so when we are doing a training, most pattern recognition or machine learning algorithms, we are using this kind of terms: true positive, true negative, false positive, false negative. Anybody familiar to these terms? Maybe you might have heard of about this one in other course, right? Okay. So let's consider this example. Now we are focusing on face detection, right? So let's say we have a classifier. Yes, it's very similar to logical gates, but it is more specific, meaning for training. Okay. Similar. Yeah. So let's say we have a classifier. Okay. Whatever. Okay. When you input a face image to your classifier, and the result is face. Oh, you gave a face image to the classifier system. By the way, the result of the classification is, oh, it is saying it is face. Is that the correct answer or wrong? Is that correct? Yes, it's correct, right? Very obvious. So face, when I input face and it is saying result is face, so this case is true positive. Okay, so here the term positive is about the result. Oh, the result of this classifier is positive. Yes. Okay. Oh, it is face. Yes. So the classifier is saying a positive answer. Okay, that is positive. By the way, this classification is correct. Okay, so on the left column here, true means, oh, this classification is true. So this is, by combining these two terms, true and positive, we call this case as true positive. So simply saying, when I give face and the classifier, okay, so if the classifier is 100% perfect, then for the face, we will always say face. Yes, yes, it is face. Okay, but mostly, classifiers are not 100% perfect. So sometimes, as for the face input, we can say face, or sometimes non-face. Anyways, in case when the classifier is saying face, I input face, classifier say yes, face. Then this case is called as true positive. True positive. So again, it means, oh, the classifier produced a positive answer. Here the positive means, because our target is face, right? So positive means the classifier say face. And by the way, this answer is correct. That is true. So true positive. Is it clear? So face input, face output. That is true positive. That is correct answer. And it is positive answer. Clear? Okay. So let's look at the next case. True negative on the right side here. The second column. Oh, by the way, you input a background. So consider the scanning process. Okay, sometimes the window will include background image instead of face. Okay. Oh, but you don't know what it is. If it is background, it is face, you don't know yet. Okay, so you input the background image to the classifier. Then, by the way, the classifier say, oh, it is not a face. It is saying a negative answer. Okay, so in this case, output is non-face, negative. Oh, it is not a face, negative. Okay, and input was non-face. So for non-face image, the classifier is saying non-face. So in other words, for background image reason, the classifier is saying, oh, it is not a face. Okay, non-face to non-face. So the answer is negative, and this answer is correct. Is that correct? Yeah. So in this case, we call it true negative. True negative. Okay, true negative. Is it clear? Okay, so true negative. So the meaning of true negative is, oh, it is the classifier is saying negative answer, and it is correct. It is true. Okay. So the third one, by the way, when I input background reason, non-face image. Okay. Yes, non-face image. By the way, the classifier is saying face. It is positive answer. Is that correct or wrong? In this case, non-face from non-face to face. It is wrong answer. Okay. So it is false. This answer is wrong. So in this sense, we say false positive. So the classifier is saying positive, but not correct. So this is called as false positive. Wrong answer. Wrong positive. The false means wrong. Okay. And the other case, by the way, when I input face, the real face, but the classifier cannot say it is face. The classifier is saying it is non-face. So the answer is negative, and this answer is wrong. So in this case, the last case, false negative. Okay. So maybe some of you are familiar to this, but I wish everybody understand these stuff. We have 4 different cases. By the way, when we are studying this algorithm and especially this machine learning process, we need to understand these 2 terms, especially true positive and false positive. Okay, true positive, false positive. So if the classifier is saying true positive showing the result of true positive a lot, it means it is good system. Okay, because that is the correct answers. By the way, if the system is generating false positive a lot, what does that mean? Yes, high error. So false positive means error. Okay. So when we have too many false positives, it is a bad system, bad classifier. Yes. Okay. So true positive is good, false positive is bad. Okay. So when we are designing the learning system, okay, our purpose is to achieve very high true positive, okay, and very low false positive. Okay. So true positive should be very high, and false positive should be very low. Okay, so that is the target of the training learning system. Okay, so in this sense, you will see a lot. The main process is targeting, to increase the true positive and to decrease false positive, especially when we are studying the cascaded, process. So these two terms are very important. Okay, so please keep in mind, these two terms. Okay, true positive, high true positive, very very low false positive is our target for the training, for the learning system. Is it clear? Any question? Okay, all clear? Okay, then let's move to the next concept, supervised and unsupervised learning. So this is also very well-known concept for pattern recognition, pattern classification, okay, and any kind of machine learning algorithms. Okay, so do you guys all understand these two concepts? What's the difference between supervised and unsupervised? Anybody can answer? What's the main difference? Supervised and unsupervised? Yes. Yeah, good answer. Yeah. So unsupervised, we don't know include label. It means, in case of supervised, we know the label. Okay, label. Yeah, we can say label. And our said, supervised is automatically done by machine. Yeah. So when you say automatically done, the labels are not given by the user or engineer, by people, and the system is trying to give the label automatically. Okay. Yeah. That's good. So in case of supervised, as you said, okay, so we are giving the label. So we know which one is face, which picture is non-face. So each one is positive sample, which one is negative. So these two terms, positive, negative, these are terms used to represent the samples. Okay, so this sample is also kind of very popular keyword when we are representing this kind of training data. So the sample, one sample means one image in our image kind of process, image training system. Okay, so one sample, it means one face image. So we are collecting many samples. Okay, many face images. So positive samples means many positive. Here positive means our targeting object. In this case, it is phase. If you are training car detection system, then you have to have positive samples of cars. Okay, so in this case, positive samples means phase images. So as you can see in this picture, okay, in the database, we have a lot of phase images. Okay, and negative samples means just non-phase. Non-phase, from the images that is not phase. It doesn't need to be any specific object. It can be tree, it can be chair, it can be desk, it can be book, whatever or object other than phase. Okay, so this is non-phase objects, non-phase samples, non-phase images. So formally, it is called negative samples. So in this way, when especially like this binary, classifier, when we say binary, it means we want to say yes or no, or phase or non-phase. Okay, so we just have two categories to classify. Okay, so every category, phase, non-phase, we know which input sample is positive, which is negative. So we are giving this information to the training system. Then the training system is designed to use this information, positive, negative. That is supervised learning or training system. Okay. So in case of unsupervised, we are not giving this information. We just input phase images. We just input non-phase images, positive, negative, all as one database. Okay. So we don't give that information. So this unsupervised learning system does not have those information. Which one is positive, which one is negative. But by analyzing kind of some feature space and the feature distribution, the unsupervised learning is to distinguish these two objects automatically. Okay, that is kind of unsupervised training learning system. Okay, so your question is blur images can be taken in negative samples. Okay, so it depends on how much blur, right? But normally, so when we say blurred image, it means it is not too much, just a little bit blurred. So normally blurred images are in positive samples. So sometimes we intentionally generate some blurred images. Okay, but it is still depending on your intention or your design of the system. Okay, for example, I don't want to classify blurred images, blurred faces as face. I want to make the results for classify them as non-face. Then you can put blurred image to the negative samples, but it is not usual. Is it clear? Okay, thank you. Okay, so this is very general, concept of supervised and unsupervised, learning system. And this algorithm, Cascade AdaBoost, is using supervised learning system. Okay, so it means to train this, algorithm, you have to provide positive samples and negative samples separately. Okay, so this is its phases, this is non-phases. So we have to give the label. Okay. Okay. So and let's discuss about cascaded detection process. Okay. So again, this cascaded classification structure or process is one of the key, contribution of this paper. Okay. So the cascade means, we'll study about this approach later, maybe tomorrow. Okay. So later or next week, okay, maybe. But we'll study in detail about this one in detail. But let's discuss very briefly for now. Okay. So the cascade means the stages. Cascade is actually composed of stages. Okay. There are several stages, like 20 or 30 kind of stages, and the stages are processed by a sequence of classifiers. So cascade is composed of stage. By the way, here, every stage means every classifier. Okay? So instead of making one big classifier, so this cascade approach is dividing the big classifier into a smaller classifiers, and then they process it one by one as a sequence. So it is basically essentially very similar to decision tree classification system. Okay. Yeah, by constructing the classification system in this way, dividing every small classifiers into small classifiers, then it is making it can make this whole classification system more efficient. Okay, so we see what it means. When the main idea is when any classifier, here any classifier means the stage, right? Every stage is composed of a classifier. So at any stage, the corresponding classifier rejects, oh, this is not phase, then we don't need to go further. So we don't need to go to the next stage. So this is how cascade classifier is designed. Okay, so in this way we can increase the speed, efficiency of the classification. Okay, yeah, so let's discuss about the details later. Okay, so anyways, this is the main purpose of cascaded, classifier system. Okay. Okay, so there was kind of very overall concepts, the general concept you need to know before we go to the detail algorithm. Okay, so now we are going to start from the very beginning part of this algorithm. The first part is the feature. So just even before the main training process, learning process, we have to calculate the feature first. So the features of the input image data should be prepared. So what kind of features are we going to use? So for example, we can use a color feature. We can use a frequency domain kind of feature. So we can use any local features, shape features, or texture features, right? So in this way, we have to determine the feature first. Actually, the learning system, even the cascaded ADA boost, okay, that is all talking about the learning process. So what is the positive samples? What is the negative samples? Okay? It is just learning system, but it is not just dependent on the feature. So it means we can use any type of features if it is good. Okay, so using the same learning process, learning system, we can give different features. So the learning system is just training the given feature from the feature calculation kind of module. Okay, so in practice, we can give different types of features. But in this algorithm, they are using this specific feature, hard-like feature. Okay, so we'll study about hard-like feature. But again, it is not directly related to the learning process itself. The learning process actually, learning algorithm actually don't care what kind of feature you're using. What they're interested in is, how this feature, whatever it is working. Is it a good one? Is it bad one? Does it have large error or high accuracy, whatever? Okay, that is more important for the training system itself. Okay, so anyways, in this paper, they are using hard-like feature. So when they say hard-like, it means this hard, HAAR, is very traditional, very old, very well known and very traditional and very old type of feature among representing kind of the texture. Actually, is kind of very simple texture feature. So it is giving us the information about the pattern of some reason, small reason. Okay, that is HAR. Okay, HAR function. So this HAR-like means it is kind of very simplified HAR feature. So they say it is HAR-like feature. Okay, and so this is very another kind of new one, very popular, kind of feature, and very relatively compared to very uh, recent high-level features, it is kind of a little bit low-level features. Okay, so but the main contribution of this paper is by providing by giving this integral image, they could speed up the process of this HAR-like feature calculation. So traditionally, we just calculate HAR-like feature in a kind of very general way, very normal way. Okay. In this paper, they propose the integral image that can process this HAR-like feature very quickly. Okay, we study how it is done. Okay. Okay. Let me go to the next one. So first of all, let's see what is HAR-like features. So if you search, HAR-like feature, you can see many documents and web pages. So it should be very easy to understand it. It's not a kind of difficult feature. Okay, very straightforward. For example, we are defining this HAR-like feature using rectangles. Okay, so inside the picture, for example, in this first picture, inside A picture, it can be kind of face or non-face. Okay, whatever. It is normally sample image. Sample. Okay, here the sample means sample for training. So it can be face or non-face. A small image. Okay. Inside this small image, we place, for example, two rectangle feature. In case of two rectangle feature, we place two rectangles. By the way, one rectangle is white. Then the other rectangle is black, white and black. So in case of A, okay, the white and black rectangles are laid out kind of horizontally. Okay, white on the left, black on the right. Okay. In case of B, white and black are laid out vertically. So white is lower, bottom, black is top. Okay. So in this way, we can lay out two rectangles in different ways. So every different combination can generate different features. So by the way, then what is the meaning of white and black? So basically, it is very simple feature. So it is calculating the difference between the sum of these two regions. So this A rectangle, it means actually picture. So normally it is gray image. So let's say it is face. Okay, face image. Then white area, white region is plus. Black rectangle region is minus, negative. So we are subtracting from white and black area. So we calculate the sum of pixel value. Here the pixel value is gray value. Sum of all value in white region. We calculate sum of all value in the black region, and then subtract. So white is plus, black is minus. So we add them. Then it is subtraction basically. Is it clear? Okay. So basically, it is subtracting two small regions inside an image. Okay, your question is detecting corners, but it is not about corners. So in this way, we can respond to corners a little bit, but it is not designed for corners. So we cannot detect corners in this way. So we have some other corner detector, everything, right? Okay, so in this sense, okay, so It's a good question. When you say corner, corners are like kind of local point features, right? They can be used for local invariant features. So this kind of popular feature. By the way, this hard-like feature, it cannot detect corner, right? So it cannot give us information like, some invariant feature or corner. It means this hard-like feature is much lower level feature than corners. Is that clear? So it is a little bit related to edge features. You know what is edge? Everybody they understand edge, right? If you know some image processing, edge. So edge points means there is some position point where the brightness is changing a lot, right? So for example, when you are calculating this highlight feature in the background area, the white background, okay, then if you subtract this white region and black region, then what is the result? It is exactly white region. Then if you calculate this feature, the subtraction, white and black, what is the result? Can you guess? Can you calculate it? 1. Okay. Any other question? Other answer? So we are assuming, the size of white and black are the same. Okay. Any other suggestion? No? Okay. So when we apply this feature on top of the white region, okay? Yes, 0, 1 or 0. Okay. So the sum of white region may have some large value, right? The sum of black region may also have large value. By the way, if their brightness of every pixel inside every region are all the same. Okay, so the sum of white region and sum of black region are the same, whatever it is. It can be a very large number, but they are the same. Then subtracting two same value regardless of the value itself. Okay, yeah, subtraction of same value is generating 0. Okay, so when this feature, for example, just in case, two rectangle feature, when they have some high value, big value, or highlight two rectangle highlight feature is generating very big value, then what does that mean? In that region, there is a big brightness gray change. There is no change, or like the white image, okay, or any black, whatever. Okay, same color region, same brightness region, then the result will be 0. But when there is some change in that region, then the result will be big. The subtraction will give us any big value. Is it clear? So in this sense, we can say it is kind of, edge highlighting, kind of similar to edge, but not exactly edge. So as we already know, there is some good edge, algorithms, but it is not exactly for edge. Even, by the way, this highlight feature looks a little bit similar to edge, vertical edge or horizontal edge, but it is still lower level. So for edge processing, we are doing some more, convolution kind of processing, right? But this highlight feature is much more, lower level kind of feature. So it is just subtracting. It is not considering the direction, whatever. Okay. So in this sense, very simple feature. So these two examples are just examples. So vertical, horizontal layout, two rectangles, black and white, can generate different features. By the way, even in case of A, even with the same horizontal layout, left, white, right, black, okay? Even with the same size. By the way, if we move this to other position, then is it the same feature or different feature? Just changing the position of white and black. It is becoming different feature because we are calculating the difference. Yeah, not same, right? Because we are calculating the subtraction in different reason. So, for example, if you are calculating this subtraction in eye area of the face, or in the same size, we are doing the subtraction in the mouth area. They will show some different value, right? So in that sense, even for the same image, same face image. So in that sense, the position of this two rectangle feature can give us different feature, different value. So they are regarded as different feature. So just even moving the same size, two rectangle, or horizontal rectangle, okay? By moving them, we can generate different features, okay? In case of B, the same way, it is also obviously, different feature, and just moving the position, changing the position also can give us every different feature. By the way, what about the size? If you change the size a little bit, half size, half height, okay, then it is definitely different feature. They will generate, different feature value, okay? So changing size, changing, direction, like horizontal, vertical direction, and changing position. All these kind of variations can generate different, features. So when we say two rectangle feature, this is just a category of one category of feature. They are composed of two rectangles, but by changing size, position, and direction, we can generate a lot of much more number of features inside this one category. Is that clear? Okay. And the next step is three rectangles. By adding one more rectangle, okay, so we have two white and one black, horizontally or vertically, and even different size. So this is one category, another category, but inside this three rectangle feature, we can generate a lot of detail every feature. Someone asked a question about the standard for size and position, right? There is no kind of standard kind of stuff, but it cannot be too small and it cannot be too large, but it depends on your implementation. Okay, so when this paper is proposing this one, they define some minimum size and maximum size, blah blah blah. But every implementation, you can change a little bit considering the performance. You have to find the best configuration. Okay, but the one important thing is you have to provide diverse size and position and direction. That's more important. It doesn't change. Okay. Okay. So every category, two rectangle feature, we may have thousands and 10,000, kind of features. Three rectangle features by changing size is a kind of combination, right? Different size, different position, okay, different direction. It's a combination. It can generate a lot of features, many features. And we have one more category, four rectangles. We add one more rectangle. So it is composed of to white to black in this way, right? As diagonal position. Okay. So again, this is one category. Inside this category, we will have many different sizes and different position, blah blah blah. So we can also generate many. 4 by 24. Here, the base resolution means the size of the sample image, so base or non-base image when we are doing the training. Okay, because we are calculating this feature for the given training samples. Okay, so the base resolution is 24 pixel with 24 pixel height. That is the size of A or B or C rectangle image, the big rectangle in this slide, for example. Okay, so considering 24, then the exhaustive set of rectangle. Here, the exhaustive set, it means it is a kind of combination of different category, different size, different position, different direction. Okay, all combination can generate over 180,000 different features. So just using these three categories, 2 rectangle, 3 rectangle, 4 rectangle, you can generate 180,000 different type of features. That's the basic starting point for the training. So we are assuming we have so many, over 100. It's not exactly right, but depending on the size and position. But we have over 180,000 features ready for training. By the way, some of them is good, some of them is not good. Some of them, it means some of them useful for training, some of them is useless. Okay. So in the training process, the AWS algorithm will try to select some good features among this large set of features, 180,000 features. That is the main first goal of AWS algorithm. Okay, but we are starting with this number of features, so many features. Okay, is that clear? So this is about highlight feature. Okay. In the next page, now for this prepare, we have to prepare these highlight features in advance. Okay. Then, by the way, to calculate this subtraction, so the main process, calculation of highlight feature is just subtraction. Okay. Sum, addition, and subtraction, because we have to calculate the sum of white region. We have to calculate the sum of black region. Okay, so we need addition of many pixel values. Okay, and then we have to do subtraction. So subtraction is not so many, right? Subtraction is just subtraction of the sum value, but this calculation is not so many. But the addition is happening a lot. So this is actually taking the performance, the time of this feature calculation. So to reduce the time of addition, this paper is proposing integral image. Okay, so we'll see how integral image can reduce the time of addition dramatically. Okay, so we're by the way, I think we'd better have a break. We didn't have a break yet, so let's have just 10-minute break, and let's continue with integral image. Okay, is that clear? Okay, thank you. Let's have 10-minute break. So it's maybe 10:43. Yeah, let's start 53. Okay, region 53. Thank you. Okay. Okay, so let's talk about integral image. Okay, so this integral image is just for hard-like feature. Okay, to speed up the process of the feature calculation, especially the addition process. Okay, because in case of hard-like feature, there are lots of additions to calculate the sum of every region again and again and again. Okay, when you consider many features, right? So it is redundantly calculating the sum of region again and again and again. Okay, so to avoid that kind of redundant, some addition of gray value, pixel values. Okay, so this integral image is proposed. You can dramatically reduce the time of redundant addition. Okay. So theoretically, so this formula is representing, the integral image, II. So II means integral image, okay, II. And so the right side, so this is kind of sum of I, X prime, Y prime, blah, blah, blah. Okay, so this, it is kind of formal mathematical formula. Okay, so let's see how we can calculate, this integral image. So basically, the concept of integral image. Okay, by the way, let me ask you this: is there anybody familiar to integral image already? No. Okay. Yeah. Okay. So then let's talk about it in detail. So the concept of integral image is literally, it is every pixel is integral value. So normally when we have image, right? So every pixel is representing the gray value at that position. Okay. The integral image means, every pixel, every position has the integral value. So it's basically the sum of all previous pixels. Okay. So I think write better, this is kind of a formal process, but I'd better, show you the next page first. Okay, let's talk about this next page. Okay, so let's see this very small image region. Okay, so the real actual image is much bigger, but to understand it easier, let's consider this small image region. Okay, in this case, every value is representing every pixel value. So again, pixel value means gray. Okay, so we have 9 pixels in the original image. 1, 2, 5, 3, 4, 6, 7, 8, 9. So this is 9 pixel value of this image, simplified image. By the way, let's consider the position of 8. Okay, 8 position. I am now at this, third column, third row, and second column position, 8. So the pixel value is 8 originally. Okay. So by the way, the integral value of this position is represented as this, red rectangle. This red rectangle. So it means that instead of just 8, the integral value at this position is sum of all these red rectangles. So this red rectangle is representing, the row number that is less than or equal to the current one, 3. So it means 2, 0, 1, 2, okay, 1, 2, 3, okay? And the column number is less than or equal to the current one. So it is representing this area from position 8. Okay, so this is the area for integration. So sum of the integral means sum basically, right? Sum of all this value of this region 1, 2, 3, 4, 7, 8 is becoming 25. So 25 is replacing current position 8. That is integral value. Yeah, okay, I understand what you mean, right? So here, why we are using just 2 columns, right? Because the position 8 is the second column. So we are just, the row and column should be, the maximum row and maximum column should be the current position. Okay, is that clear now? Okay, let's think about another case then. Okay, let's think about position in original image. Okay. Oh, you didn't understand why? Okay, so let's consider another example. Okay, let's think about. Let me change the color, and let's think about 6. Okay, position 6. What is the corresponding integral value of 6? 21 in the integral image, right? So let's see how it can be calculated. Okay, so now we are at the position 6. Then the column number, okay, so you get 1, 3, 8, 4, 10. No, I'm sorry. So, it is calculated using original image, not from the integral image. Yes, exactly. So SIS is correct. Yes, exactly. Yeah, right? Okay. So we are now in the third column, right? So we are using 1, 2, 3 column, including current one. Okay. And row, we are in the second row. So we are using 1, 2 row. So this box is becoming integral region. Okay. So we are adding 1, 2, 5, 3, 4, 6. It is becoming 21. Is that clear? Is that clear now? I think, yeah, our understood. Oh, 3, 4, 6, 7, 8, 9. 3, 4, 6, 7, 8, 9. Yeah, it's impossible. So in case of 9, so let me change the color to blue. Okay, in case of 9, okay, we have to use the 3 column and 3 row. Okay, it means all the pixels. So there is nothing like starting from the middle, like 3, 4, 6, 7, 8, 9. Is that clear? That is integral. So it is becoming larger if you go to right. Okay, it is becoming larger. If you go to down, it is becoming larger. So the last number, like 45, is the largest sum. The whole sum of this small image. Okay, the last value, okay, right bottom value is sum of all the region of the original image. Okay, again, the sum, this integral is calculated based on original image. We are not summing from the integral image. Is that clear? Yes, we are starting, always we are starting from 0, 0 for any position. Okay? Okay, thank you. Okay, so with that concept, let's look at the previous page. I want to go to previous page. Okay, so this formula is representing that concept. So x prime, y prime, sum, right? Sum x prime is less than or equal to x, y prime equals less than or equal to y. Okay, so this way we can calculate the sum of the given region, column and row. Okay, so to calculate, by the way, when you are implementing this integral image calculation, so when the original image is given, the grayscale image is given, then from that given original image, you have to calculate the integral image. So in terms of algorithm, we can use this kind of recursive computation. It is very straightforward. Firstly, we accumulate the rows, different rows. For example, sx comma y equals sx y minus 1 plus current ixy. So it means it is vertically calculating the sum first. Okay, and then ii is added horizontally. Okay, adding horizontal value. So in this way, vertical sum and horizontal sum. Finally, we can get ii. Okay, so that is kind of very systematic recursive computation to calculate this integral image in practice. Okay, so this is just a detailed algorithm to calculate this one, but I think the concept is more important, right? What it means. Okay, so I believe all of you have understood the concept of integral image. Okay, let's go. Then, now we have integral image, right? Then how can we use this one for highlight features? Again, especially the addition process. So again, highlight feature should add the sum, okay? To get the sum of the region, we have to add all the pixel value, okay? So, by the way, instead of original image, if we have integral image, okay? So, for example, in this example, in this slides, so I'm looking at slide 13, just in case. So, I want to sum this D region, D, okay, region D region, okay? Then, without integral image, okay, what we have to do is we have to iterate all the pixels gray value and add, right? Depending on the size of this width and height, we have to do many addition. Okay. By the way, sorry, if we have integral image, so for example, so this is example. If the value is simply 10, 10, 10, 10, okay, 10, 10, 10, it is the size of B is 5 pixel width and 3 pixel height. Okay, how many pixels? 15, right? 15. So the sum of this region is becoming 150. By the way, to generate this number, how many additions do you need to do? Then we have 15 pixels in the region. How many additions? Maybe just in terms of addition operation, 14. Yes, 14. Good. Okay. Okay. So let's consider this situation using the integral image. Okay. So for example, we have this A region and B region in the next page. So let me move to the next page. Okay, A region and B region. The hard right feature F equals B subtract A, because B is white, A is black, right? So B is plus, A is minus, so B minus A. That subtraction is becoming F. By the way, to calculate B region, for example, first, B region, okay? So let's guess, it is composed of 15 pixels, like the previous one. Then we have to do 14 addition. By the way, if we have integral image, this is integral image on top of integral image, then we know the position of B, rectangle, okay? Then here is 3, 4, 5, 6 means every integral value of the corner of B, okay? Then the rectangle sum, the sum of this rectangle inside in the integral image is represented as 6 minus 5 minus 4 plus 3. Can you guess, how it's working? Okay, so 6 means, okay, let me draw this line. 6 means all the sum until 6 in terms of row and column. Okay, so it says all the sum. By the way, B is included inside, 6 integral region. Yeah. Okay. But 6 includes B. Okay. So we have to subtract, some, unnecessary region. Okay. So from 6, first of all, we subtract 5. Let me change the color. 5. Okay. Let's subtract 5. 5 means this region. This region. Okay. Oh, we cut this region, but still it is more than B. Okay. Okay. So I want to subtract. Let me change the color. I want to subtract 4 because I know 4 value. So 4 means this green region. Okay. Okay. So this means 6 minus 5 minus 4. Then I guess I can get B region sum. Okay. Okay. 6 represents the sum of all the blue region. Okay. And 5 means the sum of all the red region. 4 means sum of all the green region. Then I want to have this three regions, some of the three regions. That is a basic calculation. By the way, when we are subtracting 5 is red and 4 green, you know, this yellow, I think yellow, okay, so let me, this purple, okay, this purple region, purple region is subtracted twice, okay, 3. So this purple region sum is 3 actually in integral image, okay. So we are adding 3 again, once more, because it was subtracted twice. It is supposed to be subtracted just one time, but this region is subtracted twice when we are subtracting 5 and 4. So we should add 3. So finally, we have the correct B region sum. That is the way to calculate the sum of region B. Is that clear? So in this case, how many calculations is happening here? So 2 subtraction and 1 addition. So 3. 2 subtraction, 1 addition. Okay? So instead of 14, it's much less than 14. When the region is bigger, then this calculation is much smaller. So it is always 3 operations, whatever the size of the region. Even though the size of the region, the number of pixels in the region is 100, then we should do like, in the original image, we should do 99 addition. But now, using integral image, we need to do 2 subtraction and 1 addition. That's it. Because we know the integral value already for every position. Yes, I agree. Yeah. So, by the way, to do this, right? To do this, we have to, anyways, we have to prepare the integral image in advance, right? Okay. Yeah, I agree. So it takes some time to calculate the integral image. It is another kind of sum, right? You have to, as we have discussed already, you have to do some addition, right, to calculate the integral image. By the way, let's consider this one, in case of calculating, integral image, we are calculating the sum just one time. Okay. By the way, if you don't use integral image when you are calculating the features, sometimes in many cases the features are overlapping in terms of region. It means you are calculating addition again, 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 and again. So it is redundant addition happening for the overlapping region. Is that clear? So using this integral one, okay, we just calculate the sum of the whole integral just one time. And then every time you calculate the feature, it is, just doing 3 operations. So it is, in practice, much less time to calculate this feature. So it is one important point, okay, contribution of this paper to make this algorithm almost real time, many frames per second. Okay, if you turn off this feature, then the speed is becoming much slower. Okay, there is another factor, to make this algorithm very fast, but this is one important step that is making this algorithm very fast. Okay, is it clear now? Okay, so that's it. It is about integral image. Okay, and highlight feature. So highlight features are calculated in this way in this paper. Any question? So this is actually the first step. The next step is about the training, AWS training. Okay, good. Good. Okay, let's go to the next, AWS training. So I think we have about 15 minutes, so I think we can do some introduction today. And tomorrow we'll discuss more in detail. So this page, I'm now looking at page 16. Okay, so this page is showing the overall, overview of the learning process. Okay, so in the beginning of the learning, we are assuming we have the prepared feature set. Okay, the feature set is prepared based on the highlight feature. Okay, so in terms of highlight feature, as we have already discussed, we have over 100,000 rectangle features. Rectangle, for rectangle, all of them. Okay, 100,000 based on size and position. Okay, so this is the feature set. So it means this feature set are kind of all possible candidate features we can use for our system, but we are not using all of them finally. Okay, so what we are going to do, especially in this second step of AWS training, is to select just a few. Like here, when we say a few, it is like about some thousand. Okay, like for example, 2,000 from 180,000 is much less than 180,000, right? Okay. So we want to select just some thousands of good features among 180,000 features. Okay, so this one big feature set is ready in advance. Okay, then the learning process. In the learning process, we are using this term weak learner, weak classifier. Okay, so every feature, every 180,000 feature is becoming weak classifier, weak learner. Okay, and then we try to select with weak learner, weak classifier, and then our target is to generate the final strong classifier. Okay, yeah. And for this learning process, we also need another database of training set. So the training set means training data set. It is composed of positive samples. The positive samples means face images, and negative samples non-face images. Because again, it is supervised learning. Okay, so feature set is now ready, training set is ready, then the learning process is working with this feature set and training set, and try to generate weak classifiers by selecting weak features, and then based on the selected features, it is generating final strong classifier. So finally, the strong classifier can classify this complicated, feature face and non-face, feature space. So we can divide face and non-face. So we can classify face and non-face. Okay? So this is just the overall overview of the system. Okay. So again, AWS learning algorithm, the main purpose is feature selection. That is the main task of this algorithm. Okay, so let's remember this, basic, setup. Okay, so now let's consider a little bit more about the general pattern classification. So about feature, in terms of feature. So what is then? Okay, so the main purpose of AWS is to select good features. Then how can we know what is good and which is good, which is not good. Okay, so then let's see this example. This is very common, concept of good features and bad features. Good features and bad features. So, by the way, you can determine, good feature and bad feature based on the sample images, because we already know the positive samples and negative samples, because this is supervised learning, right? We are assuming they are given with the label, face and non-face. Okay. Then let's consider the left graph, the black one. Okay, the black one. Let's consider two features, F3 and F4. Okay. So for every, positive and negative samples, so in this example, I plotted, positive sample as red and negative sample as white. Okay. So for positive sample, for example, F3 is one of the highlight feature. So highlight feature is subtraction value basically, right? Using interval image, whatever. Okay. Then the highlight feature can generate just one number. Okay? One number, one subtraction value, one value. So F3 has one value per every image, sample image. F4 also will generate another one value for every sample. Then, for example, for face, every face sample image, I apply F3 highlight feature. Then I can plot the value position of every sample like this. Oh, this one is this position, the other one is this position, in this way. Okay? And F4, I calculate the same samples using different, F4 highlight feature. Then you will have, this Y value, Y axis value. Okay? In this way, this is, just one example of feature space of F3 and F4 as a combination. Okay, so this is the distribution of the samples in this feature space, F3 and F4. So we have red dots, okay, red position for positive and white position for negative. By the way, in this black graph, the red positive and white negative samples are all mixed together. So we cannot find any clear line, distinguishable line between red and white. Okay? So this is not a good feature. So in this case, you can say like, oh, F3 and F4 both not a good feature, because they cannot distinguish positive and negative samples clearly. Is it clear? Okay. By the way, let's look at the right graph, the blue one. Okay. Feature F1 and F2. Okay. I plotted, the positive face image and negative image in the same way, the red dot and white dot. Okay. Then, in case of F1, then I apply F1 feature, for example, like this kind of vertical to rectangle highlight feature. Okay, then it will give us one value for every image. Every image can have some different value, right? So if this is a good feature, okay, then we can say like, for example, the face samples can have very small values, subtraction values, like this. And so these are, taking, small position. Okay. But negative samples has, high, big value in this case. So F1 is dividing positive and negative using this vertical line. Clear? And F2, in the same way, the by the way, in case of F2, the positive phase samples has big value like this, big value, and negative white, small value. So this horizontal line can divide these positive and negative samples. So it means, these features, F1 and F2, they are good to distinguish this, positive and negative. So in this sense, we can say it is good feature. Okay. So your question is this assuming that all training images have the same projection and appearance? No, because they have different appearance and different positions. So we can see, different position in this feature space. If they have the same, for example, every face has same appearance, then they may have just one position in the feature space, right? Their subtraction value for any feature will be the same for every sample, okay? So every face, some face is for male, some face is female, baby, whatever, every different person, if I apply, even though I apply the same feature, they can generate a little bit different, value. But if the feature is good, if the feature has very good position and good size, okay, to represent the face area, then the value will be very similar. They will take very near position. So it means it is easy to distinguish the positive and negative samples. Okay. So another question, F3 and F4 are bad features. Yes, exactly. So in this sense, F3, F4, they cannot distinguish. So if I just mandatorily, draw this kind of line, oh, I want to classify. Okay, some big one is face. That's a small one is non-face. Okay, then this classification will generate very big error. Okay, but in case of F1 and F2, if I draw the line in this vertical and horizontal line for classification, oh, if the value is larger than this line, the value is bigger than this, smaller than this line, then I want to say it is face or non-face. Okay, then the error will be very small. Okay, so this is the way we select the feature. So we can actually the direct way to select a good feature is we are calculating the error. So we are we try to select this kind of classification line value. This is kind of threshold value for every feature. Okay, so I draw this line. So this value is becoming a value threshold. So if the feature value for F1 is less than this line value, threshold value, then it is determined as positive face. It is larger than this value threshold, it is determined as non-face. But sometimes some non-face may be in this left side, right? Or sometimes the face will be on the a little bit right side. Then they can be an error. Yes, yeah, by examining the classification region, right? So sometimes fail, sometimes succeed, right? So how many samples are successfully classified? How many samples are wrongly classified? Okay, then if we calculate the ratio, then we can determine which is good, which is bad. Okay. I'm looking at the question right now. The interface between F1 and F2 can be line as it can be used as provide upgrade. Okay, so there is another question from Otara in the air slide. Okay, So normally to generate this kind of line, we are using some linear kind of classification, kind of linear formula like AX plus B, like kind of stuff. But in this case, in this algorithm, so because we are using very simple classifier, the highlight feature. So it is just threshold. So it is like every feature is stacked individually. Okay, first. Okay, so we just look at F1 and we say, oh, if it is less than the sample value is less than the threshold. In this case is vertical line. So this is just vertical or horizontal, actually. Okay, less than some value, then it is phase. Larger than this value, it is non-phase. So for F2, if it is larger than some value, it is phase. If it is less than some value, it is non-phase. So in this way, the classification is done individually, for every feature. So in other words, we are considering every feature as every individual small classifier. Is it clear now? Okay. So we consider every feature as every very small and simple classifier, and by doing some classification, so based on the threshold, okay, then based on the result of classification, we try to measure if it is good or bad, how much good or how much bad, based on the error case, the ratio of the error. Because we know which one is phase and which one is non-phase already, because again, it is provide learning. So we can calculate the error, very easily based on the result of classification. If the result of classification is correct, so when I input phase, it is saying phase based on the threshold, then it is success. By the way, when I input phase, it is saying non-phase, it is fair. Okay, so we are calculating the error rate in that way. So we are trying to select the best good features based on the classification error. And small error is good feature. Okay, so I think that's for today. Okay, so tomorrow we'll continue this process more in detail. How we actually can calculate the error in detail. What kind of formula and in what way how the detailed training algorithm is working. Okay. Any final question? All good? Is everything clear now? Okay, so then see you tomorrow morning. Okay, and let's discuss more in detail. Oh, by the way, anybody has read the paper? This paper? Anybody? Can you show up? Not yet. Okay, so you know the paper, right? It is open in internet. So oh yeah, good. So just reading the paper may be a little bit difficult, right? But still, if you read together with this lecture, then it can be easier for you to understand the paper. Okay, so it's very helpful if you read at least the kind of introduction and the early part of the paper. If you don't have much time, okay, it's not a kind of task or kind of stuff, but try to read the paper. Okay, it can be helpful. Okay. Thank you very much again, and see you tomorrow. Okay, we are going to use the same slide tomorrow. Okay, thank you. Bye bye.